This is second video on kinematics of rigid body. You need to look at first video before you can get hang of this. Now here we are going to discuss specifically instantaneous center method. By this method you can solve any problem which you may come across in this exam scenario. So method goes like this. First you have to understand what is instantaneous center. So instantaneous center is a point whose velocity is zero at the instant of interest. You see, this is a little difficult to conceive, but when body is moving, it's possible to have at least one point which will have zero velocity at that particular instant. Now, this point need not be inside the body. Instantaneous center may be inside or outside the body. That's okay. That's okay. We take instantaneous center as reference point so that working gets simplified. This is the crux of the matter. If you have seen last video, we have found velocity of any point on the rigid body using a reference point whose velocity was known. Now the idea is we find the instantaneous center whose velocity is zero anyway and use that as a reference. So then finding velocity of any other point becomes very easy, as will be demonstrated towards the end of this video. Now see, last video we have taken this problem wherein a wheel is rolling and center's velocity, which we have taken as a reference point, is known as 1.5 meter per second, and the angular velocity of the wheel is known, and we worked out velocities of all these different points on the circumference. That's what we did. Now what I'm going to do is I'm going to do the same problem with instantaneous center method so as to demonstrate why we use it and how easy it will be. So first of all, you should know what is instantaneous center for this wheel. Now see, look at the wheel. The bottom point, as you can see, we have worked out, has a zero velocity, but then you need not work out, since it is touching ground, that point which touches grounds at that instant has a zero velocity, and that is instantaneous center. So particularly for this type of problem where wheel is rolling, the instantaneous center without solving the problem is known as the point which touches the ground. Now, what we are going to do is we are going to take the same data. That is radius is 0.75 meter, omega is 2, that is angular velocity is 2 radians per second, and this point, the bottom point, is the instantaneous center. Now my task is to find velocity of a point on the circumference. How we do it for rigid bodies is that point has two velocities. One, velocity of reference, other, velocity due to rotation. That is rotation, you have to think that this point is rotating about reference point. So for that purpose we join this line. We work out length of this line, which is by simple geometry, because the radius is 0.75, this will come to 0.75 root 2. Now velocity of the point on the circumference will be velocity of reference point, which is zero velocity because it's a instantaneous center, and r omega. So r omega is in this case 0.75 root 2 and omega is 2. So it is 1.5 root 2, and direction perpendicular to this r because it is r omega. It's as if this point is moving around in a circular path about the reference point. So this blue colored velocity, blue arrow shows direction, and the magnitude is 1.5 root 2 of the velocity of the point on the circumference. Now we have worked out in this manner. Earlier we had worked out it like this, and if you calculate 1.5 square plus 1 square under root, you will get this velocity again. So answer is obviously same, only method is different. I'll demonstrate it with the point diametrically opposite. I join the line again I work out the distance and do r omega because it's a clockwise motion of the wheel. The arrow is upward, magnitude is 1.5 root 2, and answer earlier we got this, which is same as what blue arrow tells us. Similarly, the top point, what you do, you join reference point to the top point. The distance is 0.75 plus 0.75, 1.5. So velocity is 1.5 into 2 r omega, that is 3, which was same as earlier. You remember this? This and this is same, only thing we have worked it out with instantaneous center. So as you can see, if you know the instantaneous center, then all you have to do is join the instantaneous center with the point of interest and you get your velocity. So the crux of the matter is, if in a given problem, if you are able to find the instantaneous center, then we can move further. Again, in the same problem, look at the center's velocity. We can easily find what is the distance from the bottom to center. It's 0.75. 0.75 into 2 is 1.5, which, if you remember, was the velocity of the center in this problem when we solved it earlier. So now let's see how to find instantaneous center. I mean, in a problem which is new to us. So let's say here is a wheel, it's not touching ground. Okay, so you don't know where the velocity, but it's moving ahead and rotating. And let's say somehow I find this instantaneous center I. Then velocity of any point at a distance r1 will be r1 omega. At any other point r2 will be r2 omega. Now suppose I didn't know instantaneous center, but somehow, due to where the rotation or some data is given, I know velocity direction of these 2 points. Then all I have to do is I draw perpendicular to these 2 velocities and I get my instantaneous center. So what is the method for finding instantaneous center? If you know, of course, if you know 2 velocity directions, I mean that is velocity directions of 2 points, not the magnitude, mind you, just the directions of 2 points on the rigid body. From that it's possible to find instantaneous center. And once you have instantaneous center, as you can see, as you have seen already, you can find velocity of any other point. Now this video I'll devote to learning how to find instantaneous centers in different situations. For example, if I have a ladder sliding, that is A moving towards right and B moving down, I want to find instantaneous center. If I know these 2 velocity directions, which I'm sure it's easy to see because A has to move to right, then B has to come down. Drop perpendicular to these velocities and here you have instantaneous center. So for a simple body sliding, you can find in this manner. Now look at a problem like this where there are 2 links, and for these bodies AB and BC, for both I want to find instantaneous center. How do I do it? Well, for AB you realize that A is hinged, and by the way BC, C is a roller like thing which is moving towards right. So for AB instantaneous center, because A is hinged, obviously it is A because that has a 0 velocity. For BC, how we find out is like this. Look at BC. Surely C's velocity direction is known to us, and B's velocity direction, if you think that B is on AB and A is instantaneous center of AB, then it will be perpendicular to AB like this. I'm not talking about magnitude, I'm just talking about direction. And now look at B as point on BC, member BC. Then I know velocity of B, I mean velocity direction of B, I know velocity direction of C, and we draw perpendicular to these 2, I get my instantaneous center. So look at B carefully. At B what I have done, I have drawn perpendicular to AB to get velocity direction, and then I have drawn perpendicular to this velocity again. In other words, I just extended AB and then drawn perpendicular to velocity at C, and I got my instantaneous center. Let's do one more type. Here there are three links. Here there are three links. So in this case then, AB, BC, CD, and say I am required to find velocity centers of all three. See, AB is simple, A is hinged, so A is velocity center. CD is simple, D is hinged, so D is velocity center. And for BC, you do exactly same thing. Think BC as point on AB, so you have velocity direction as in blue, colored arrow. Similarly, C you think it is on CD and you know velocity direction is horizontal because CD is vertical. Now you think B and C as points on link BC. You know two velocity directions, so you know how to handle it. Draw perpendicular to the velocities. And the beautiful part is, for the first link and the last link, essentially you are just extending the links, because at B you are drawn velocity perpendicular and again perpendicular, means AB is extended, and CD same thing at C. You are drawn perpendicular to C, and for the velocity, and again drawn perpendicular. They meet at I, and that's the velocity. That's the velocity. That's the instantaneous center. So three links is very simple. Extend the into links, and you get velocity center of the middle link. Last type let's do, and that is, let's say there is a circle and there is a rod, and let's say at B it is allowed to go up, and circle or a cylinder is moving in a clockwise direction towards right. Look at it. Cylinder touching ground, so velocity center of cylinder is the bottom. For AB, B's velocity is up, A's velocity is towards right, horizontal, because if you look at cylinder, join velocity center of cylinder to A, it's a vertical line, so A's velocity is horizontal line. I know on AB two velocity directions, I draw perpendicular, and here I have the velocity center I. Now you see, to my mind, these are the only four type of problems which you really need to do. So what you will learn in this video is how to find instantaneous center. In the next video, we are going to actually solve these problems. Thank you.